Hello there, and welcome back to the Sleepless Scientist, your quiet corner of the cosmos where curiosity meets calm, and science gently rocks you to sleep. Before we begin our celestial journey tonight, I'd love for you to take a moment to notice where you are. Feel the support of your bed beneath you, the softness of your pillow, the gentle weight of your blanket holding you in a safe embrace. Perhaps you can hear the faint, distant sounds of the world outside settling down for the night, the whisper of a passing car or the sigh of the wind. Or maybe the only sound in your world is the quiet, steady rhythm of your own breathing. It always fills me with a sense of wonder to think of us all, listening together from different corners of the globe, connected in this peaceful moment under the same vast, starry sky. For some of you, the moon might be high in the sky, a silent silver witness to your rest, while for others, the first gentle hints of dawn may be painting the eastern horizon. Yet here we are, sharing this gentle journey, each in our own cozy spot. A small, invisible community of dreamers exploring the universe from the comfort of our beds. If you enjoy tonight's voyage into the cosmic deep, consider giving this story a gentle like, or perhaps subscribing to join our next stargazing session. It helps more sleepy minds find their way to this quiet harbor, and it ensures you won't miss any future dreamlike journeys through the universe. But for now, there is no rush at all. The universe has been waiting for billions of years. It can certainly wait for you to get comfortable and find your perfect position for rest. Tonight, we are going on a journey to the most mysterious and misunderstood objects in the entire universe. They are places where our understanding of physics seems to bend and break, where time and space behave in the most peculiar and wonderful ways. We are going to drift toward the deep, quiet mystery of black holes. We'll begin by watching the birth of a black hole, not as a violent event, but as the magnificent, transformative final act of a giant star's life. Then we will gently explore its anatomy, from the silent point of no return to the swirling, luminous halo of light that surrounds it. A paradox of perfect darkness, ringed by brilliant light. We'll imagine what it might be like to travel near one of these cosmic titans, where time itself slows to a crawl and space bends like a river. We'll discover the different kinds of black holes that exist, a whole family of them, from the common stellar variety to the gentle giants that anchor entire galaxies, including our own beloved Milky Way. We'll learn how astronomers, in their patient and clever ways, manage to find these invisible objects, listening for their faint whispers across the fabric of spacetime itself. And finally, we will travel trillions upon trillions of years into the far, deep future to witness the slow, peaceful end of a black hole as it gently evaporates, returning everything it ever took back into the cosmos in a final, quiet sigh. I hope the story is just interesting enough to capture your imagination, but so gentle and soothing in its telling that it guides you effortlessly and peacefully toward a deep and profound sleep. So, settle in now. Let your shoulders drop away from your ears, releasing any weight they may have been carrying from the day. Unclench your jaw and let your tongue rest gently in your mouth. Take a slow, deep breath in, filling your lungs with calm, cool air. And as you breathe out, feel any lingering tension, any worry or thought melt away with your exhale. Feel the gentle rhythm of your breathing in and out, a quiet, steady clock within you, a soft and personal metronome. You are about to drift on a journey to the very edge of reality itself, carried softly on words and imagination. There is no need to hurry. Each moment will unfold at its own gentle pace. Outside, the world is hushed and still. Let your mind become as quiet as the night around you. The deep, dark, and wondrous story of black holes is waiting for us, and it will be our guide as we drift toward a peaceful, restorative sleep. Let us begin. To understand where a black hole comes from, we must first look to the stars. Imagine, for a moment, the vast, silent theater of the night sky. Each star you see, each tiny pinprick of light, is a colossal bowl of hot gas, a nuclear furnace burning with incredible power for millions or even billions of years. At the heart of every single star, a constant, silent battle is being waged. It is a battle between two of the most fundamental forces in the universe. On one side, there is the immense, relentless force of gravity trying to crush the star inward, to pull all of its vast material down into a single, infinitesimally small point. It is a patient, unyielding force, always pulling, always squeezing. On the other side, fighting against this constant pull, is the tremendous outward pressure generated by the nuclear fusion in the star's core. Deep within the star, atoms of hydrogen are being fused together to create helium, releasing a tremendous amount of energy in the process. This energy pushes outward, like the heat from a fire pushing back the cold. For most of a star's life, these two opposing forces are in a state of perfect, serene balance, a delicate cosmic equilibrium. The star is stable, shining steadily, a reliable and beautiful beacon in the darkness of space. But just like anything that burns fuel, a star cannot shine forever. Its life, however long it may be, is finite. Eventually, the fuel in its core begins to run out. For a star like our Sun, a relatively small and common star, the end of its life will be a relatively peaceful and graceful affair. When its hydrogen runs low, it will swell up into a red giant, its outer layers expanding far out into space. Then, over thousands of years, it will gently puff away these outer layers, creating a beautiful, glowing nebula of gas and dust. What will be left behind is a small, hot, incredibly dense core called a white dwarf, no larger than the Earth, which will then spend the rest of eternity slowly cooling down, like a fading ember from a long-extinguished fire. But for stars that are truly massive 10, 20, or even 50 times more massive than our Sun, the end of their life is a far more spectacular and dramatic event. And it is in this magnificent, breathtaking finale that a black hole can be born. Let's imagine one of these cosmic giants. It has lived a brilliant but fleeting life, burning through its vast reserves of fuel at a furious rate. For millions of years, it has been one of the brightest and bluest lights in its galactic neighborhood, a true celestial king. But now, its time is coming to an end. Deep in its core, it has fused lighter elements into heavier ones, from hydrogen to helium, then carbon, oxygen, and all the way up to iron. Iron is the final ash of stellar fusion. Fusing it does not release energy, it consumes it. The nuclear furnace at the star's heart begins to sputter and die. The outward pressure that has held the colossal force of gravity at bay for millions of years suddenly vanishes. Gravity, the patient, relentless force that has been waiting all this time, finally begins to win the long battle. The star's iron core, which can be as large as our own Earth, but contains the mass of several suns, suddenly has nothing to support it. In less than a single second, an event of unimaginable scale and speed unfolds. The core collapses catastrophically under its own immense weight. It implodes, crushed by a gravitational force so powerful that no known force in the universe can stop it. As the core collapses into a point of unimaginable density, the vast outer layers of the star, all that gas and plasma that made it so large and bright, suddenly lose their footing. They come crashing down toward the center at incredible speeds, a significant fraction of the speed of light. When this cascading material hits the newly formed, ultra-dense core, it rebounds in a titanic, explosive shockwave. This is a supernova. For a few short weeks, the single dying star can outshine its entire home galaxy, which contains hundreds of billions of other stars. It becomes a beacon of light visible across the universe, a final, glorious burst of energy that sends the heavy elements forged in the star's heart, elements like oxygen, carbon, gold, and platinum, scattering across the vastness of space. These precious elements will drift through the cosmos for eons, eventually mixing with clouds of gas and dust to become part of new stars, new planets, and perhaps, one day, new forms of life. It is a beautiful thought that the very iron in our blood and the calcium in our bones were forged in the heart of a dying star long ago. But as this beautiful cosmic firework fades from view over weeks and months, our attention returns to what is left behind at the very center of the explosion. If the original star was massive enough, the collapse of its core does not stop. It doesn't form a dense object like a white dwarf or even a superdense neutron star. The pull of gravity is so overwhelmingly, incomprehensibly powerful that it crushes the core beyond all known limits of physics. It squeezes all of that matter, a mass several times that of our own sun, into an infinitely small, infinitely dense point. A point where our human concepts of space and time, our familiar laws of physics, simply cease to make sense. This point of infinite density is called a singularity, and the region of space surrounding it, a region from which nothing, not even light itself, can ever escape, is what we call a black hole. Think of it not as a violent death, but as a profound and quiet transformation. The star has shed its bright, shining, visible form and has become something new, something quiet, dark, and mysterious. It has retired from the visible universe, leaving behind only its immense gravity, a silent, powerful echo of the giant it once was. It's a peaceful thought, in a way. A massive, brilliant star, after a long life of pouring light out into the cosmos, collapses into a point of perfect darkness and ultimate stillness. It has become a permanent, gentle shadow on the fabric of the cosmos, a place of profound mystery, born from a final, beautiful burst of starlight. As you lie here, breathing softly and slowly, imagine that magnificent star, its life's journey complete, giving way to this new, quiet form, a serene and mysterious black hole born from light, now a master of darkness. Now that we have witnessed the quiet birth of a black hole from stardust and fire, let's allow our minds to drift a little closer and gently explore its structure. A black hole is not a hole. In the way we might think of a hole in the ground, it is not an empty void. It is, in fact, an incredible amount of matter, an immense mass, packed into an impossibly small, perhaps even zero-sized, space. And because it is so incredibly dense, its gravitational pull is stronger than any other force in the universe. Let's look at its different parts, not as terrifying or dangerous features, but as wondrous and fascinating aspects of this deep cosmic mystery. At the very heart of every black hole, hidden forever from our view, lies the singularity. This is the point we spoke of earlier, where the entire mass of the collapsed star's core is crushed to a state of infinite density. It is a place so extreme, so far beyond our everyday experience, that our current science and mathematics cannot fully describe it. The words we use to navigate our world, up, down, left, right, before, after, lose their meaning here. Space and time, as we know them, are thought to warp and cease to exist in a conventional sense. It's best not to think of it as a scary or threatening place, but rather as a point of pure mystery, a cosmic question mark at the very edge of our human knowledge. It is hidden from us, forever veiled from the outside universe, because to see a singularity, we would have to cross the black hole's most famous and most misunderstood feature: the event horizon. The event horizon is not a physical surface. You could not stand on it or touch it. It is an invisible, spherical boundary, a one-way door in space. It is the ultimate point of no return. Imagine yourself in a small boat on a wide, powerful river that flows toward a massive, inescapable waterfall. As you float down the river, the current gets stronger and stronger. For a while, if you have a powerful enough engine in your boat, you can still turn around and fight the current to escape. But there is a certain point, a line in the water right at the edge of the falls, where the current becomes too swift and powerful. Once you cross that line, no engine in the world, no amount of power can save you. You are destined to be carried over the edge. The event horizon of a black hole is precisely like that point in the river. It is the boundary where the gravitational pull of the black hole becomes so overwhelmingly strong that the escape velocity, the speed needed to get away, is greater than the speed of light. And since nothing in the universe can travel faster than light, anything that crosses the event horizon can never, ever leave. Light, radio waves, dust, stars, or hypothetical spaceships, once they cross that invisible line, they are pulled inexorably inward toward the singularity at the center. Their journeys end now sealed for a black hole that is spinning. And we believe that most, if not all, of them do. There is another fascinating region just outside the event horizon called the ergosphere. The word ergo comes from the Greek word for work, and this is a place where the black hole's tremendous rotation has an incredible effect. A spinning black hole doesn't just curve spacetime, it actively drags spacetime around with it, like a spinning bowl submerged in honey would drag the honey around in a swirl. This effect is called frame dragging. Inside the ergosphere, space itself is flowing around the black hole faster than the speed of light. This doesn't mean things inside are breaking the cosmic speed limit, because it's space itself that is moving. But it does mean that inside the ergosphere, it is physically impossible to stand still. You would be forced to move in the direction of the black hole's spin, no matter how powerful your rocket engines were. It would be like trying to stand still in a furious whirlpool. The current of spacetime itself is just too strong. It is a mind-bending concept, a region where space itself is a flowing, inescapable current. But let's imagine we are a safe distance away, just observing. As matter, like gas and dust from a nearby star, gets drawn toward the black hole, it rarely falls straight in. Because of its own momentum from its previous orbit, it begins to spiral around the black hole, much like water spiraling down a drain or a planet orbiting the sun. This spiraling material forms a vast, flat structure called an accretion disk. And this is where a beautiful and stunning paradox emerges. The black hole itself is the darkest thing imaginable, a perfect absorber of all light, yet the region immediately surrounding it can be one of the brightest and most luminous places in the entire universe. As the gas and dust in the accretion disk swirl ever closer to the event horizon, they are accelerated to incredible speeds, approaching the speed of light. The immense friction between the particles of gas heats the material up to millions of degrees, causing it to glow with incredible brilliance across the entire electromagnetic spectrum, from low-energy radio waves to visible light, and all the way up to incredibly powerful X-rays and gamma rays. So when astronomers look for a black hole, they often don't look for darkness. They look for this incredibly bright, ferociously hot, swirling disk of light, a luminous halo surrounding a perfect circle of pure blackness. It's a stunning sight to imagine. A vast vortex of brilliant, superheated gas, a cosmic whirlpool of light, dancing gracefully around an abyss of perfect, silent darkness. There is one more ghostly and beautiful feature to explore in the anatomy of a black hole. Just outside the event horizon, there is a very special, precarious orbit known as the photon sphere. This is a region where gravity is so intensely strong that photons, the very particles of light, can be trapped in orbit. A ray of light, if it enters this sphere at just the right angle, will not fall in and will not escape. Instead, it will be forced to circle the black hole forever in this unstable, knife-edge orbit. If you could somehow stand, unmoving, within the photon sphere and look straight ahead, you would be able to see the back of your own head. This is because the light from the back of your head would travel all the way around the black hole and arrive back at your eyes from the front. It is a place of captured light, a ghostly sphere of looping images, where photons from across the eons are forced to dance in a perpetual, silent orbit around the edge of darkness. So a black hole is not just an empty void. It is a central singularity of deep mystery, an event horizon that marks a quiet one-way threshold, an ergosphere of flowing spacetime, an accretion disk of brilliant, fiery light, and a photon sphere of orbiting ghosts. It is a complex and strangely beautiful structure, a serene and powerful testament to the most extreme forces at play in our wonderful universe. As we drift here in our thoughts, safe and sound in our beds, let's allow our imagination to take us on a hypothetical journey close to a black hole, to feel how it warps the very fabric of reality itself. Albert Einstein's revolutionary theory of general relativity tells us that massive objects don't just pull on things with a mysterious force of gravity. They actually bend and curve the four-dimensional fabric of spacetime around them. And no object in the universe does this more dramatically or more profoundly than a black hole. First, let's consider the strange effects of its gravitational pull. As you get closer to a black hole, the tidal forces become immense. Tidal forces are not the pull of gravity itself, but the difference in the gravitational pull across an object. Here on Earth, the Moon's gravity pulls slightly more strongly on the side of the Earth facing it than on the far side. And this difference is what stretches the oceans and creates our high and low tides. Near a black hole, these tidal forces are taken to an unimaginable extreme. If you were to imagine an empty spaceship falling toward a small, stellar mass black hole, the gravity pulling on the front of the ship would be so much stronger than the gravity pulling on the back that the ship would be stretched out, becoming longer and thinner, like a piece of spaghetti. This process is poetically, if a little grimly, known as spaghettification. It's not a violent tearing in the usual sense, but a fundamental stretching of space itself, with the object simply being carried along for the ride. For a very large, supermassive black hole, however, the kind that lives at the center of galaxies, these tidal forces are much weaker at the event horizon because the gravitational slope is more gradual. An object, or even a person in a spaceship, could cross the event horizon of a supermassive black hole without being stretched apart at all, only to be inevitably crushed much later as they approach the singularity at the center. Another beautiful and mind-bending effect of a black hole's gravity is gravitational lensing. As we've learned, a black hole's gravity bends spacetime, and light must follow these curves. This means a massive object like a black hole can act like a lens, a giant cosmic magnifying glass, or a funhouse mirror. If a black hole happens to pass directly in front of a distant star from our point of view, its gravity will bend the light from that star around it, focusing it toward us. From our perspective on Earth, we would see the distant star suddenly and smoothly brighten, and then fade back to normal as the black hole moves away. This is called microlensing. In more dramatic cases, if the alignment is just right, the light from a distant galaxy directly behind a black hole can be bent into stunning, distorted shapes. We might see multiple images of the same galaxy, or its light might be smeared into beautiful, glowing arcs, or even, in the case of perfect alignment, a complete and perfect circle of light known as an Einstein ring. It creates a warped, beautiful window onto the universe behind it. But perhaps the most wondrous and profound effect that occurs near a black hole is what happens to the passage of time. As Einstein predicted, gravity warps not just space, but time as well. The stronger the gravity, the slower time passes relative to a place with weaker gravity. This effect is called gravitational time dilation. It happens everywhere in the universe, even here on Earth, though the effect is so tiny in our daily lives that we never notice it. A clock at sea level, where gravity is slightly stronger, will tick ever so slightly slower than an identical clock on top of a high mountain. Over a lifetime, the person on the mountain would have aged a few microseconds more than the person at sea level. But near the intense gravity of a black hole, this effect becomes profound and dramatic. Let's imagine our two twins again, both astronauts on a deep space mission. One twin stays on a large mothership, orbiting at a very safe distance from a supermassive black hole in a region where time passes normally. The other twin takes a smaller, faster ship and decides to go on a short expedition to orbit very close to the black hole's event horizon for a while. For the twin near the black hole, in that deep gravitational well, time would pass much more slowly. They might spend what feels like just 1 hour orbiting the black hole, listening to some music, reading a chapter of a book, and admiring the view of the swirling accretion disk below. But when they fire up their engines and return to the mothership, they would find an incredible shock awaiting them. For their twin who stayed far away, decades or even centuries might have passed. The orbiting twin, by dipping into that region of slow time, would have effectively traveled far into the future. From the perspective of the distant observer on the mothership, the twin near the black hole would appear to be moving in extreme slow motion. As their ship got closer and closer to the event horizon, it would seem to slow down more and more, its light becoming dimmer and redder due to the gravitational redshift, until it appeared to freeze just at the edge, suspended in time for all eternity. They would never actually see it cross the boundary. This bending of time is a deep and beautiful mystery. It tells us that time is not a universal constant, not a steady, cosmic drumbeat that is the same for everyone, everywhere. Time is relative, it is flexible, it is part of the physical fabric of the world and can be stretched and compressed by the gentle hand of gravity. To think that there are places in the universe where time itself almost grinds to a halt is a profoundly humbling and wondrous thought. As you lie here, feeling the steady, normal passage of time in your room, the gentle and reliable rhythm of your own breath, you can find comfort in this steady pace. And you can also feel a sense of awe, knowing that out there, in the deep cosmos, time itself is dancing to a different, slower, more majestic tune, slowed to a near stop by the immense, quiet gravity of a black hole. Black holes, we have learned, are not all the same. They come in a fascinating variety of sizes, from relatively small to mind-bogglingly large. Just as there are many different kinds of stars in the night sky, from small red dwarfs to giant blue supergiants, there is a whole family of black holes, each with its own origin story and its own unique role in the grand cosmic ecosystem. Let's gently meet the members of this mysterious and dark family. The most common type, and the one we have already discussed, is the stellar mass black hole. These are the black holes born from the supernova explosion and subsequent collapse of a single, massive star. They are typically between 3 and perhaps a few dozen times the mass of our own sun. While that sounds enormous to us, in the grand scheme of the cosmos, they are relatively small. Their event horizons would be only a few miles across, the size of a small city. Our own galaxy, the Milky Way, is thought to be home to tens of millions of these stellar mass black holes, the silent, invisible remnants of long-dead giant stars. Most of them drift through the darkness of interstellar space alone, completely invisible and quiet, their presence unfelt unless something gets very close. We can only find them if they happen to be in a binary star system with another star, siphoning off its gas and creating that bright, hot accretion disk that gives away their hiding place. They are the commoners of the black hole family, scattered throughout the galaxy like dark, hidden jewels. At the other extreme end of the scale, we have the gentle giants of the universe, the supermassive black holes. These are the undisputed titans of the cosmos. They are not just hundreds or thousands, but millions or even billions of times the mass of our sun. We now believe that nearly every large galaxy, including our own Milky Way, has a supermassive black hole at its very center, acting as a kind of stable, gravitational anchor around which the entire galaxy revolves. The one at the heart of our galaxy is called Sagittarius A*, pronounced A star. It has a mass of about 4 million suns, yet its event horizon is still relatively small, small enough to fit comfortably within the orbit of the planet Mercury in our solar system. These giants were not born from the collapse of a single star. They are far too massive for that. Their origin is one of the great unsolved mysteries in modern astronomy. Perhaps they formed from the direct collapse of gigantic clouds of gas in the very early universe. Or maybe they started their lives as smaller black holes that grew over billions of years by merging with other black holes, and by feasting on the steady stream of stars and gas clouds that wandered too close to the galactic center. Instead of thinking of them as destructive monsters, it is more accurate to see them as a fundamental and even creative part of a galaxy's life. They are the calm, quiet heart around which everything else revolves. The billions of stars in the center of our galaxy, including our own sun in its distant orbit, are all part of a slow, graceful cosmic dance around Sagittarius, a asterisk. A dance that has been going on for eons. These supermassive black holes are not just passive anchors. They can also act as cosmic gardeners. As they feed on surrounding gas, they can launch powerful, narrow jets of energy and particles from their poles, which travel out into the galaxy for tens of thousands of light years. These powerful jets can plow into vast, cold clouds of interstellar gas far away, compressing them and triggering the birth of new generations of stars. So, in a beautiful, cyclical way, the death of matter falling into a black hole can lead directly to the birth of new stars elsewhere in the galaxy. Between these two extremes, the very small stellar black holes and the very large supermassive ones, scientists have long searched for the middle children of the family, the so-called intermediate mass black holes. These would be hundreds or thousands of times the mass of the Sun. For a long time, we weren't sure if they even existed, as they were incredibly difficult to detect. But recent evidence strongly suggests they do, perhaps hiding in the dense, crowded hearts of ancient star clusters known as globular clusters. They may be the missing link in the story of black hole evolution, the seeds from which the supermassive black holes eventually grow over cosmic time. And finally, there is one more hypothetical and very strange member of the family: primordial black holes. These are not thought to be formed from collapsing stars at all. Instead, it is theorized that they could have formed in the very first second after the Big Bang, when the universe was incredibly hot and dense. In that chaotic early environment, tiny fluctuations in density could have been so extreme that some regions collapsed directly into black holes. These primordial black holes could be of any size, but some could be incredibly tiny, perhaps with the mass of a mountain or an asteroid, but compressed to a size smaller than a single atom. We have not yet found any definitive evidence for them, but it is a fascinating idea that the universe might be filled with these tiny, ancient relics from its very birth. So, as you drift here in the quiet of your room, you can picture this celestial family. The millions of small, quiet stellar black holes wandering the galactic arms like silent ships. The mysterious intermediate ones, hiding in the hearts of ancient star clusters. The tiny, hypothetical primordial ones, ghosts from the dawn of time. And at the very center of it all, the serene, supermassive black hole, the silent, gravitational heart of our galactic home, holding everything together in its gentle, unwavering, and peaceful grip. One of the most intriguing and challenging things about black holes is that they are, by their very nature, completely invisible. They emit no light, no heat, no radiation of their own. So how can we be so sure that they exist? How do astronomers find something that cannot be seen? The answer is a beautiful exercise in cosmic detective work. We don't look for the black hole itself. We look for the effects it has on the space and the things around it. It's like trying to find an invisible person walking in the snow by looking for their footprints. The footprints of a black hole are written in the light of distant stars, in the motion of galaxies, and in the very fabric of spacetime itself. One of the first and most powerful ways we found evidence for black holes was by patiently watching the motion of stars. In the center of our own Milky Way galaxy, for instance, astronomers at observatories around the world meticulously tracked the orbits of several stars for many, many years. They saw these stars whipping around a single, empty point in space at incredible speeds, some moving at several million miles per hour. It was clear they were orbiting something, but when they looked with the most powerful telescopes, there was nothing there to see. By precisely measuring the shape and speed of these orbits, they could use the laws of gravity to calculate the mass of the invisible object they were circling. The result was astounding. The object had a mass of 4 million suns, all packed into a tiny, completely dark space. The only thing that could be so massive, and yet so completely dark, was a supermassive black hole. It was a beautiful and elegant piece of detective work, proving the existence of an invisible giant by simply watching the graceful dance of the stars around it. Another important way we find black holes is by seeing the glow of their accretion disks, as we discussed earlier. When a stellar mass black hole is in a binary system with a normal star, its powerful gravity can pull a stream of gas from its companion. This stolen gas doesn't fall straight in. It forms that hot, glowing disk that shines with incredible intensity, especially in high-energy X-rays. Our powerful X-ray telescopes in orbit high above the Earth's atmosphere can scan the skies for these bright sources of X-ray light. When we see one of these X-ray sources, and we can also see a normal star orbiting it, but the source of the X-rays itself is invisible. It's a very strong sign that a black hole is hiding there, quietly feeding on its neighbor. A more subtle and beautiful method of detection is through the phenomenon of gravitational lensing. As we've learned, Einstein's theory tells us that gravity bends light. A massive object like a black hole can act like a cosmic lens or a magnifying glass. If a wandering black hole passes in front of a distant star, its gravity will bend the light from that star around it, focusing it toward us. From our perspective on Earth, we would see the distant star suddenly and smoothly brighten for a short time, and then fade back to normal as the black hole moves away. Or in the more dramatic cases we imagined earlier, the light from a distant galaxy can be bent into a beautiful, distorted arc, or even a perfect Einstein ring. By observing these strange, warped images of distant objects, we can infer the presence of an invisible massive object, the black hole, acting as the unseen lens. But the most revolutionary and direct way we now see black holes is by listening to them. Not with our ears, of course, but with remarkable scientific instruments called gravitational wave observatories. Gravitational waves are ripples in the fabric of spacetime itself, first predicted by Einstein over a century ago. When two massive objects, like two black holes or two neutron stars, are locked in a close orbit, they spiral into each other and eventually merge. This cataclysmic event creates a colossal disturbance in spacetime, sending powerful ripples outward across the universe at the speed of light. These ripples are incredibly faint. By the time they reach Earth, having traveled for billions of years, they stretch and squeeze the very space of our planet by a distance smaller than the width of a single proton. But our incredibly sensitive L-shaped gravitational wave detectors, with lasers running down miles-long tunnels, can sense this tiny, fleeting distortion. For the first time in human history, we can hear the sound of two black holes merging billions of light years away. Each detection is like hearing a tiny, rising chirp, the final sound of a cosmic ballet. Listening to these faint whispers from across the universe is a profoundly peaceful and awe-inspiring experience, connecting us directly to the deepest, most mysterious, and most powerful events in the entire cosmos. We have journeyed to the fiery birth of a black hole and explored its long and influential life. Now, for the final leg of our drowsy exploration, we take a momentous step, drifting far, far into the deep, dark future, to a time almost beyond human imagination, to witness the quiet and peaceful end of a black hole. It seems like a paradox. If nothing, not even light, can escape a black hole, how can it ever possibly end? For a long time, it was thought that black holes were truly eternal, the final, indestructible resting places of matter. But one of the greatest and most imaginative physicists of our time, the late Stephen Hawking, discovered something incredible, a subtle flaw in their apparent perfection. Black holes are not completely black. They evaporate. This astonishing process is known as Hawking radiation, and it is a result of the strange and wonderful rules of quantum mechanics playing out at the very edge of the event horizon. In the seemingly empty vacuum of space, pairs of virtual particles are constantly popping into existence and then annihilating each other almost instantly in a continuous, quiet fizz of creation and destruction. Normally, this has no net effect. But if a pair of these particles happens to appear right at the event horizon of a black hole, it's possible for one of the particles to fall in while the other one manages to escape into space. To an outside observer, it would look as though the black hole has just emitted a particle. The particle that escapes carries away a tiny, tiny amount of energy from the black hole. And since energy and mass are equivalent, as described by Einstein's famous equation E equals mc2, the black hole loses a tiny amount of its mass. From the outside, it looks as if the black hole is slowly radiating heat, like a piece of hot coal very, very, very slowly cooling down. Now, this process of evaporation is incredibly, mind-numbingly slow. For a typical stellar mass black hole, the rate of evaporation is so tiny that it would take an unimaginably long time for it to disappear completely. We are not talking about billions or even trillions of years. We are talking about something like 10 to the power of 67 years. That's a 1 followed by 67 zeros. This number is so astronomically large that it makes the current age of the universe, 13.8 billion years, seem like less than a single, fleeting heartbeat. For a supermassive black hole, the timescale is even longer, closer to 10 to the power of 100 years, a number so large it is called a googol. Let's imagine this far-flung future, this twilight of the cosmos. The universe is ancient, cold, and profoundly dark. All the stars have long since burned out and faded away. The galaxies themselves have dissolved, their dead stars scattered by countless gravitational encounters. The universe is a vast, quiet, and nearly empty place, a diffuse soup of cold particles and faint, dying radiation. And in this immense, eternal darkness, the last remaining complex objects, the last relics of a brighter age, the black holes, are slowly, gently evaporating. Over eons that defy all comprehension, they lose their mass, drop by drop, particle by particle. As a black hole gets smaller, its temperature increases and its rate of evaporation speeds up. In its very final moments, a tiny stellar mass black hole would release all of its remaining energy in a final, quiet, but powerful flash of light and high-energy particles. Like the last ember of a great cosmic fire, finally going out with one last, soft pop. And then there is only silence and darkness. The black hole is gone. Its mass and its energy have been returned to the universe. This is perhaps the most peaceful and poetic ending imaginable for these cosmic titans. These objects, born from the spectacular collapse of giant stars, which consumed matter and light for eons, do not last forever. They too are part of the great, endless cosmic cycle. They slowly, patiently, and completely give back everything they ever took. They dissolve back into the fabric of the universe, leaving nothing behind but faint, cooling radiation. It's a beautiful thought, a final act of ultimate cosmic recycling. It suggests that in our universe, nothing is truly permanent, not even the objects we once thought were eternal prisons for light and matter. Everything eventually returns to the whole. In that final, quiet, distant epoch of the universe, the last whispers will be the gentle sighs of evaporating black holes, a peaceful and fitting end to their long, dark, and mysterious existence. Here we are, back in the quiet safety of the present moment. Our long journey is complete. We have drifted together across the vast expanse of space and time, from the fiery birth of a black hole in a supernova to its slow, gentle evaporation in the far-flung future of a cold, dark universe. We've explored its strange and wondrous anatomy, felt the way it bends time and space, and met its diverse family of cosmic giants, from the smallest wanderers to the great galactic hearts. We learned how our clever scientists can find these invisible wonders by listening to the faint gravitational whispers they send across the cosmos. You have journeyed to the very edge of reality and returned, all from the deep safety and comfort of your own bed. Take a moment now to let these vast and gentle ideas settle. They are so large, so grand, that they can make the mind feel quiet and wonderfully still. Let the immense scale of the cosmos be a source of profound peace for you. In the face of such unimaginable spans of time and space, our daily worries and concerns can seem to shrink, to find their proper, smaller place in the grand scheme of things. You are a part of this vast, mysterious, and beautiful universe. The very same elements forged in the hearts of giant stars are right now within you. The same laws of physics that govern the slow, graceful dance of the galaxies also guide the gentle, steady rhythm of your own heart. Now it is time to let go of the journey. Let the images of swirling disks and distant stars fade away like a pleasant and peaceful dream. Gently bring your awareness back to the simple, physical sensations of this moment. The feeling of your head resting on the pillow, the gentle warmth of your body under the blankets, the soft, effortless rise and fall of your chest with each slow, deep breath. Your body knows that it is time to rest. Your mind, having been on a grand tour of the cosmos, is quiet. You have given it a wondrous journey to ponder, and now it can be still. If any thoughts should arise, just let them float by like distant, silent stars in the night sky. You don't need to follow them or hold onto them. Your only task now is to rest, to allow yourself to sink deeper and deeper into a state of profound peace and welcome relaxation. The universe will continue its silent, majestic, and beautiful dance while you sleep. Time will continue to flow, carrying you gently and safely toward the morning. Thank you for joining me for the Sleepless Scientist on this voyage into the deep. It has been a true pleasure to have your company on this gentle adventure through the cosmos. The final part of the journey tonight is yours and yours alone, the journey into deep, restorative, and peaceful sleep. Let go now. Drift off whenever you feel ready. May your dreams be filled with a quiet sense of wonder, and may you wake up feeling refreshed, restored, and at peace. Until next time, dear friend, sleep well. Good night.